All right. So you may or may not remember we talked about angular displacement and angular speed a little while ago when we were doing circular motion. Yes? Do you remember that?
Yeah.
Circular motion? Yeah? Okay. So does anybody remember what angular displacement was?
It's like how far the ray is from the starting point on the circle.
Okay, how far in degrees or radians that you've gone from your starting point. Okay, now that was helpful with the circular motion, remember, because if I have 2 points that are on a line from the center, so they're on the same radius, then as it rotates, they'll have different speeds, right? Because this one has a shorter distance to travel than that one does in the same amount of time. But the angular displacement and the angular speed will be the same, because in the amount of time it takes to go from there to there, it covers the same angular displacement. The angle that it rotates through is the same. Now, if the angle that it rotates through is the same, then that means that the angular speed is also the same. The angular speed being how fast is it rotating through that. Okay? So I wanted to make sure that we kind of remembered that first. Yes, Kate?
So the angular displacement is like the max can be like 180, it goes to 180 and then it comes back.
No, because it's how many radians have you rotated through, and it should be in radians, by the way.
Okay.
Okay?
So pi.
And so up to pi, but when you go past pi, if I start here and go to there, I've gone through pi, but I can continue going. And so it should represent how far I've actually gone. Not the angle, but how many radians I've rotated through. So if I were to start here and go around twice, then saying 0 radians is not an appropriate answer, because I've actually rotated through 2 pi twice, so it needs to be 4 pi radians is my angular displacement. Okay? If you're just talking about a distance of how far you are from one point to the other, obviously it's the same thing. The result of a 0 displacement is the same as the result of a 2 pi displacement, which is the same as the result of a 4 pi displacement. The difference is that something has gone through. Now, if you kind of think about it, back when we talked about displacement, we talked about displacement like running around a track. And if I run all the way around the track, my displacement was 0, because I started and ended at the same point on the track. Now, the idea is something occurred during that. I went through the motions of going through the track, but the displacement ended up being 0, or it was relatively the same thing. So we've got our radians there. So theta is our angular displacement. Okay, and angular displacement again is just how many radians I've rotated through. Omega, this is omega, and omega was the angular speed. Okay, so what would units of angular displacement be?
Radians.
Radians. Okay, so what would the units of angular speed be?
Radians per second.
Radians per second. Now, another name for angular speed is the angular frequency. Now, that should kind of make sense, because what are the units for frequency?
Hertz.
Hertz, which is
1 over seconds.
1 over seconds. So angular frequency is angles hertz, or angles per second, which is the same thing. Okay, so radian hertz. And you won't ever see it like that, but I wanted us to make the connection. When it talks about angular frequency, it's referring to angular speed. All right? Now, if I know my angular speed, which is in radians per second, can I calculate the period? Can I calculate how long it will take me to go all the way around? How would I do that?
1 over the angular frequency.
Okay, so 1 over the angular frequency. So what would that actually do? That would give me seconds per
Radian.
radian. So this would be seconds per radian. Is that what I want for period? What should period be? Period should be seconds per cycle. This is not seconds per cycle. Right now it's seconds per radians. How many seconds would it take me to go through 1 radian, which is only part of that circle, right? So how can I adjust this so that it matches what I want it to be? Instead of being seconds per radian, I want it to be seconds per cycle. Let's do a conversion.
2
How many radians are there in a cycle?
2 pi.
2 pi. So if I take this and I do a conversion, so this is 1 over my angular frequency, which is seconds over radians, and I multiply it by how many radians there are in a cycle, which you just told me was 2 pi radians in a cycle. The radians cancel out, leaving me with the number of cycles. So therefore, I take this and I multiply by 2 pi over 1 cycle. The units cancel out, leaving me with units of seconds per cycle, which is what the period is. And so the period, therefore, is 2 pi over the angular frequency. Now, some of you will remember that there were questions on some of the reviews and some old IB questions that asked you to make relationships between angles and period and angular. You saw this weird thing in the answer key that talked about angular frequency. Well, that's required for the AHL students. It's no longer required for the SL students. But you do need to know these, right? Because that was part of your circular motion, okay? What unfortunately you miss out on in SL is the connection then between these and your simple harmonic motion, which is what I want to cover just in the first part today, because I think it'll help kind of tie things in together and make some sense of what we have. All right? Okay, so I want us to watch this really quick, and the sound doesn't matter so much. So what do you see here?
Circular motion.
Circular motion, right? So this is going around and around, is connected to that. What do you see over here on the wall?
Oh, the shadow.
You see the shadow, right? So there's a light shining on the post, which is going in circular motion, and yet when I look at the wall, what's happening to the shadow of my post?
Moving back and forth.
Moving back and forth. And when I match it up with the pendulum, what do you see?
The exact same motion.
The exact same motion. There is a link. It's sinusoidal, right? Except what we're linking then is we're linking the motion, this motion, we're turning it into a linear motion. So we're not looking at, when I look at a circle, it has both X and Y components, right? So when I shine the light on it, I'm just looking at one component of that, the side-to-side motion. So I'm just looking at one component. And so when I just look at that one component, what I see is identical to what I see when I see the pendulum swinging. Or if I were to put a mass there on a spring going back and forth, it looks identically the same. And so there's that tie-in between the two, and we're going to use that today as we're building some relationships for period and other things, which is kind of one of the neat things we're going to do right here in just a second. So I want you to see this one as well. So this is a similar thing. So here we're going to be looking at circular motion. Okay, so a point going around essentially a unit circle. All right, here you'll see a visual of, it's just a video of a spring popping up and down, simple harmonic motion. And then what we'll see here is a graph just of height versus time. And I want you to see the relationship between this and that. Okay, now this one we're actually going to leave to go here.
We had a math question in our test for SL. They had to do it the unit circle. It was like a cylinder dumping in and out, and you graph it.
Classic.
Yeah, that's very classic in both SL and HL, a Ferris wheel or something like that, a cylinder that turns.
Does that have this do this in a way? Like the way it's graphed?
Kind of, yeah. Similar idea. We're looking at the height which when you're going around a circle, it is sinusoidal motion, the height is, because at the beginning, right, what am I doing? I'm going to pause this. Okay, so this has a constant angular speed, angular velocity. Now, we don't generally use velocity because velocity for angles is a little bit weird, because the velocity isn't to the right or left or up and down, because it's always changing as it goes around the circle. And so the velocity, angular velocity, actually has a direction either out of the page or in the page. And what that does is, if it's going around this way, if I use my right hand, if it's going around this way, then the angular velocity is considered to be out of the page, because that means that I'm going to be going around. If it's going around the other way, then we define the angular velocity to be into the page, because that means it's always going clockwise. Okay, now that's not going to be important. SL, HL, you don't need to know that. But it's just, that's why we don't talk about angular velocity, is because it has that third component in out of the page, which doesn't really mean anything to us. It just kind of helps us give an idea of the rotation. But you'll notice that as I have that constant angular speed or angular velocity, that at the beginning, it's going to make big jumps, because a small angle will mean a large difference in height. As I get closer to the top, a small angle isn't going to change it as much. Okay, and so we'll see that as we step through. So that first step, second step, so after 2 steps, you can see I'm already almost halfway up my circle there. I'm almost halfway up my curve. Now it's going to take me 1, 2, 3, 4 steps to get to the last one. So it took me twice as long almost. It's not exactly twice as long, but it took me longer to get that last half, right? Which makes sense. With the spring, it's moving slower when it gets up to the top or down to the bottom, because the force is pulling down on it, it's causing it to accelerate opposite the direction of its displacement, right? All those things that we talked about in the previous unit are all kind of coming into play, being applied here. And so again, when we play, we can see the relationship between the circular motion and our simple harmonic motion. Okay? Now, what kind of curve is this?
Sinusoidal.
It's a sinusoidal curve, right? All right, now that's going to be important. We're going to use that in just a minute. Do you see, this is important. I'm going to go forward 1 step. When it's a sinusoidal curve, at what location am I actually starting?
The bottom.
Watch. Pay close attention to where the spring actually is.
Equilibrium.
So where is it now?
Equilibrium.
Equilibrium. So if it starts at equilibrium, then I'm going to end up with a sine curve, which makes sense because its location is at 0, equilibrium. What would my graph look like if instead of starting here, I started at the maximum? So if I take my mass and lift it up just a little bit and then release it.
Cosine.
It would start at the maximum and then it would go down and back up. So it would be cosine, right? So depending on where we start, I could be using sine or cosine. So that's important to keep in mind as we go through some of the math and trigonometry that we're going to go through right now. All right, everybody okay? All right, so we just talked about this, that y was sine of, now we didn't talk about this, but this ends up being the amplitude. Sorry, not amplitude, it changes the period. We talked about how this is related to period. It's the inverse of the period, right? So we talk almost inverse because you got the 2 pi. But related to the period, so that's your multiplier there. So the height is equal to whatever the initial height was, which could be defined as 0 or whatever you want it to be, sine omega t. So this is going to be important. So if this is my definition, what is the maximum possible height?
Y0.
What's the biggest thing that sine can be?
1.
1. So if this is 1, then y0 is
The maximum.
the maximum height. Okay? So remember that because it's a little different than a lot of things that we've considered. Normally when we consider this, we say, well, y0 is the initial height. That's not what the y0 is referring to here because we said we were starting at equilibrium. So therefore y0 here is not referring to the initial height, it's referring to the maximum height because that's when sine is 1. Okay, so we're going to take note of that. So y0 equals maximum height. Not really height, it's really displacement. Sorry. Defining that to be 0, maximum displacement is actually a better way to say that.